Okay, welcome back everyone. It's a pleasure to have Eric D Hoker talk about modular graph functions. Please.
Well, thank you very much for inviting me to this conference. It's very nice to see a number of friends. I'm sorry I didn't tune in to some of the earlier seminars, but my time coordinate is lagging a little bit behind yours. So the focus of this talk is going to be string amplitudes. And I'm going to, from the outset, limit to considering only closed-oriented strings, so no open strings here. And so string amplitudes are obtained by a topological expansion in the string coupling, GS. And you're all familiar with this, this picture here. So you have tree level, you have genus 1, genus 2, and they're multiplied by various powers of the string coupling. And for every genus, you have points on the surface that correspond to the places where the vertex operators are inserted for the creation annihilation of incoming and outgoing strings. And these points are integrated over the surface. And then to get the full amplitude, you actually integrate that for each genus over the moduli space of compact Riemann surfaces of that genus. So the last integral, of course, is trivial for the sphere, but it's non-trivial for genus 1 and genus 2 and higher. So modular graph functions originally arose for a Riemann surface of genus 1. And so what are they? Well, in just one line, they map a graph, as we'll see, a certain Feynman graph, to an SL2Z invariant function of the upper half plane, which I denote by H1, of the modulus tau. These functions in general generalize real analytic Eisenstein series, and they're related to single-valued elliptic polylogs, and for that, I'll refer you to Federico's talk of yesterday. So I will briefly review this. This is all the work, really, and then move on to considering modular graph functions for higher genus surfaces. So they are maps from a graph, again, I'll specify what they are, to a function on the moduli space for genus H. And as we'll see, the simplest example of that is actually an invariant that was well known in number theory, the Kawazumi-Zhang invariant. So let me just review genus 0. So Federico already did this yesterday. For genus 0, the amplitudes are given by integrals of this type. So n is the number of vertex operators, and then z you can think of as points in the plane, or actually more precisely as points in the sphere. And they depend on kinematic variables, so-called Mandelstam variables, formed in this Lorentz invariant way out of the momenta. We're taking the external states to be massless, so k squared 0. And alpha prime is a so-called string, intercept. And you have to think of it as a very small length scale, square, or the inverse of the Planck mass or something like that, square. So effectively, for all physical processes that we know, S is a very small number, very small number. So these expressions are, by construction, meromorphic in the external variables, have simple poles at non-negative integers. And exactly where these poles are depends on the precise string theory, so I'm not going to go into that. So for example, for the 4-graviton amplitude, there is a single kinematic invariant proportional to the Riemann tensor 4 copies of it, or to the 4th, arranged in a Lorentz invariant way consistent with space-time supersymmetry. And then times a function, which I wrote down here, ratio of gamma functions, the so-called Virasoro-Shapiro amplitude. And what we're going to be concerned with most is actually its low energy expansion. So low energy means that the S's are small compared to 1. S is dimensionless, and so it makes sense to ask it to be smaller than 1. And so it's convenient to introduce these symmetric polynomials of the 3 variables S12, S13, and S14. Their sum is 0, they're not independent, but there are 2 independent ones. And so this, the expansion of this ratio gives you, first of all, a factor of 1 over STU here. So that corresponds to just the exchange of massless particles. And then all the rest is the effect of the massive string modes. And as you can see, the coefficients are nicely given by factors of the sigmas, which are kinematic invariants, and then multiplied by odd zeta values or zeta value square. And in fact, more generally, for the endpoint function, the coefficients are single valued multiple zeta values. And this has been proven not that long ago. Okay, so now let's promote to genus 1. So at genus 1, we consider a torus as the complex plane modeled out by this 2-dimensional lattice given by a modulus, tau, which lives in the upper half plane because we consider an oriented torus. So tau 2 is positive and tau 1 is an angle effectively. So the integrals we're interested in are of the following type. They're now multiple integrals over the torus, sigma, so there can be n of them, and an exponential, again, of this kinematic invariant S, and then multiplied by the scalar Green's function on the torus. Now, this is not the most general amplitude. In fact, if you go to n larger than 4, there are extra factors and so on and so forth. But this factor is universal in all string theories. So that's why we will just restrict to that, and complications can be included as we go along. So the scalar Green's function on the torus is the inverse of the Laplace operator on the space orthogonal to constants. And it's given by this double sum. So the sum is over m and n. And actually, m tau plus n is really are really the momenta on the torus. And those are discrete because the torus is a complex surface. So the Green's function g, combined in this way, integrated, is invariant under SL2Z. And if you inspect this, this quantity for given tau, you will see that it has simple poles and double poles at integers. And it is actually holomorphic in Sij in a radius of convergence of size 1. And that's because G at short, the only singularity in G is actually a short distance singularity when Z goes to 0. And that singularity is logarithmic. And so when you expand this in a power, you can integrate powers of logs just as much as you want. Now, the full amplitude, as I said before, is actually the integral of this over the moduli space of genus 1. So that's what I wrote here with the Poincare invariant, the Poincare metric on the upper half plane. Now, this last integral produces more singularities. In fact, this integral is convergent absolutely only when the real part of Sij is 0. So that's essentially a multiple line. But it was proven a long time ago that the analytic continuation exists, and if it exists, it's unique. And then I said, indeed, if you go to higher point functions, there are derivatives of the Green's functions at n, and so on and so forth. Okay, so now we're going to be interested in expanding. So this function, remember, was analytic in Sij. We're going to limit ourselves to the integrand for the moment. Later on, we'll discuss actually doing this integral. But for the moment, I'm going to concentrate on this modular function. And so this is analytic around s equal to 0. So we can actually expand in a absolutely convergent series for given tau. And this is the low energy expansion. You can organize this in terms of Feynman graphs. How do you do this? Each point Z, where a vertex operator is inserted, you represent by a dot. Each Green's function between two vertices, Zi and Zj, you represent as a line. So this is associated with the Green's function or propagator. And then you integrate over all vertices. And if you count up the number of Green's functions that occur, that we define to be the weight. So this is not the modular weight. The modular weight of this is 0 because it's SL2Z invariant, but traditionally it's given the same name, the weight. Now, graphs can be sometimes reduced. So if a graph becomes disconnected when you cut just one line, then the integral vanishes. And if you remove one vertex, then it factorizes into the products of components. So we're going to just consider these irreducible parts. So to give you an example, so if we do, for example, W is equal to 2, there are two Green's functions. There is only one way to arrange those. If you're used to Feynman diagrams as a physicist, we would say that these Feynman diagrams all have 0 external momentum. So they're really vacuum graphs. And if you go to W equal to 3, then there are 2 graphs. For W4, there are 4 graphs. And of course, you could organize this by weight, but it's actually much more interesting to organize this expansion by the number of loops. So all these graphs have 1 loop, all these graphs have 2 loops, 3 loops, and so on and so forth. This is, of course, something we're very well used to in QFT. So let's then consider first the 1 loop case. So in 1 loop, we just have a closed assembly of Green's functions. So it's this quantity. If you Fourier transform to the momenta, there's only one momentum going through the graph. And so you have the sum over the inverse momentum to the power 2w. And we'll call that function EW. So the momentum here to make contact with what we did before is given by m plus tau n, where these are integers. And actually this function, the way I normalize it, is just the real analytic Eisenstein series, EW. So it's invariant under SL2Z. It satisfies the Laplace-Beltrami eigenvalue equation with eigenvalue w times w minus 1. And it has a characteristic Laurent expansion as tau2 goes to infinity, or we go to the cusp, given by this expression, which I'm sure you well know, up to exponential corrections. So this is an extremely familiar function introduced at the end of the 19th century. All right, well, now let's go to 2-loop modular graph functions. So they were in this column here. And you see that in some sense they differ. They're all versions of taking this basic graph and then adding to some of the lines some bivalent vertices. So this is like concatenating the Green's function several times. And so you can write down an explicit expression for this as a triple sum, the 3 momenta for each line. There is a momentum conservation Kronecker delta, and then you have the product of each of the propagators raised to the number of lines you have concatenated, which we'll call AR. The weight in this case, or the number of Green's functions, is the sum of the A's. And this is again invariant under SL2Z. And actually, it's also invariant under permutations of the labels, which I'm not going to use here, but it actually plays a very important role in some of the things I will mention. So before we discussed, for the Eisenstein series, we discussed what the Laurent polynomial expansion is that it satisfies. And these functions, in fact, again, satisfy a Laurent polynomial expansion up to exponential terms near the cusp of the same range that we had for the Eisenstein series, except that now mostly all terms in between are also populated. We also looked at the differential equation, and in fact, these functions also satisfy differential equations, but not a single one anymore. Generally, they're linear combinations of the functions that satisfy differential equations. I'm just giving you the simplest ones here. So here C111 satisfies this equation. C211 satisfies this equation. They're all of the type of the Laplace operator minus an eigenvalue. And in fact, you can see just from these few examples that the eigenvalues are of the form s times s minus 1, where s is an integer. And this continues to be true to all weights. And the right-hand side, well, in this case, there is a two-loop function, but you can arrange it in such a way that all the two-loop functions on the left side, and then the right side is just linears and bilinears in the Eisenstein series. And you can prove it if holds to all orders in the weight. Now, what happens for modular graph functions at higher loop order? Well, the simplest thing one can prove is that their expansion near the cusp, when tau2 goes to infinity, is still a Laurent polynomial in tau2, so up to exponential corrections, with degree w, comma 1 minus w. Again, the intermediate powers tend to be all occupied. And the coefficients of this Laurent polynomial are in general single-valued multiple zeta values. This was conjectured in this paper of 5 years ago. And Federico showed in a simultaneous, in a contemporary paper, that in fact, these multiple zeta values include irreducible single-valued multiple zeta values. So it's not just powers and products of simple zeta values. So, so we discussed the cusp. These functions at higher loop order satisfy a whole hierarchy of algebraic relations, of which I wrote out the simplest ones. So this is a tree loop is related to two loop and one loop. For loop is related to two loop, and so on and so forth. So how you get these relations, I'm going to come to in a second. We also discussed for one loop and two loop, we discussed how the Laplace-Beltrami operator acted. That was simple for two loops. It gave you, again, a function of the same type, of two loop type, and then products and powers of Eisenstein series. This is no longer true starting at three loops. The Laplace operator simply does not send you to the same space. So what do we do about that? Well, actually, you can generalize the set of functions that you want to consider. And that was done in a paper of 4 years ago with Mike Green. And for reasons you'll see in a second, we call these objects in general modular graph forms, because they're not modular functions, they're actually forms. So in a nutshell, what do we do? Well, what happens when you apply the Laplace operator is that in the case of two loops, you see that the power of the holomorphic momentum and the anti-holomorphic momentum was always the same for every line. When you apply the Laplace operator, you get modular graph functions that cease to have this property. So in fact, the essence of this entire slide is to liberate. Oh, I'm sorry, this is an alarm. Some alarm that went off, sorry about that. So the whole idea of this slide is actually to liberate the power of the holomorphic momenta from the power of the anti-holomorphic momenta. And that's what I've written down here. So a graph, sorry about that. I don't know what to do with this thing. Okay, sorry about that. The inconvenience of giving these things from home, I guess. So what we do now is we consider a so-called decorated vertex, which is described by gamma. Gamma is a connectivity matrix, which tells you how a vertex is connected to a line. We assume that there are V vertices and R edges. And then each edge is actually decorated with two exponents, the exponent of the holomorphic momentum and the exponent of the anti-holomorphic momentum. So we put these in an array. And so here is now the function we associate with it. We raise each holomorphic momentum to the power AR and anti-holomorphic to the power BR, and then we have a momentum conservation delta function. Now, since the powers are not the same, the total powers don't have to be the same either. And so in general, this object is not a modular function. It's not invariant under SL2Z, but it transforms as a modular form. And that's just about as good. If mu isn't equal to 0, there is no canonical factor of tau2 we can put in, so you have to make some arbitrary choice. And if A is equal to B, then we just recover the modular graph functions we had before. Okay, now this space closes not only under the Laplacian, but actually under a more elementary operator, and that's the success of it. So there are actually two sets of relations between these functions. The first ones are the relations due to momentum conservation. So basically in the numerator, you can insert 0 by saying that it's the sum of all the momenta at a given vertex, and then write this out as a relation between these functions. And that gives you these relations. So in the exponents, what you do is you subtract SR. What is SR? It's an entry which is 0 everywhere, except at one point where it's 1. So you sort of go through the entire list and subtract, and then you add them all up with the connectivity matrix, and that gives you 0. So instead of considering the Laplace operator, we can actually consider the mass operator, written out on forms that have vanishing holomorphic modular weight. And this, in fact, you can easily work out and gives you that when you apply the mass operator to one of these functions, it's actually, again, a linear combination of the same type of functions with the same kind of subtractions here. And these two identities show you that, in fact, the operation of the mass operator on this space of modular forms closes. And now one can develop an algorithm for finding and then proving the validity of identities between modular graph functions and forms. And the key to this is to realize that if you want to prove an identity, let's call it F. So F would be one of these identities I wrote down here, for example. It could be more general. What you want to do is actually show the weaker condition, namely take the mass operator to the power W of F is equal to 0. So if you can show that first, then there is a theorem that allows you to go back and say that then F actually has to be a constant, and then you determine the constant from the asymptotics at the cusp. And the reason this is profitable to do this is you see that as you apply more factors of the mass operator, you remove some of the anti-holomorphic exponents and add holomorphic exponents. So at the end, in a sense, you can arrange it so that all the anti-holomorphic exponents are gone, and you're effectively left with a holomorphic modular form. And you know a lot about that. And in fact, the space of these functions is very limited. So that's the key. And this process goes under the name of holomorphic subgraph reduction and was introduced here. And in fact, allows you to find all algebraic identities between modular functions of weight 6 or less. And in fact, Gerken has written for his thesis a beautiful Mathematica program that implements this and allows you to do this concretely. Now, I should say there's a different approach to generating these identities based on generating functions and iterated integrals with, in fact, most of the people, I think, in the audience here. Okay, one last comment I want to make before I move on to genus, to higher genus, and that is that these modular graph functions have a simple connection with what we could call elliptic modular graph functions or single valued elliptic functions on sigma. So if you have them, let's take the simplest ones of these modular functions, actually just a Eisenstein series. Well, you can cut it open. Imagine that you cut one of the edges. Now you get a linear chain, but you also get 2 points actually on the torus because you cut this open. Now this object is single valued in Z by construction because it's constructed out of Green's functions. So from a modular graph functions, by suitably cutting, you can actually construct single valued elliptic functions. So these linear chains are well known. They were introduced by Zagier 30 years ago, and they generalize the Bloch-Wigner dialogue. For higher loop graph functions, this again, as I said, produces elliptic modular polylogs, and the modular functions may be recovered by setting Z equal to a special value. In this case, it's 0. For polylogs, usually they're going to be 1, but here it happens to be natural to be 0. Okay, so here I want to leave things for genus 1 and now move on to higher genus. So here I'm going to take mostly a string point of view, but also deviate from the string point of view and go into just some of the purely mathematical considerations. So how do we generalize this genus 1 formula to higher genus? Remember what the genus 1 formula looked like. So remember, this is always unintegrated over moduli. So it was an integral over n copies of the torus and then this exponential of the kinematic invariant S times the Green's function. So consider a compact Riemann surface sigma of genus H larger or equal to 2 without boundary. So what do we need? Well, we need a Green's function and we need a measure on n copies of the surface. So in other words, a natural guess is to write down this expression where G is to be found and also the measure is to be identified. So you're all very familiar with genus 1, perhaps slightly less with higher genus. So let me briefly review what I need. So the first homology group is isomorphic to 2H copies of Z. We have an antisymmetric intersection pairing matrix or form, which I'll call J. And so we can pick a canonical basis for the first homology group of A and B cycles, which I think you're all familiar with, and a canonical dual basis of holomorphic 1 forms, which I'll call omega I. And it's standard to normalize them like this on A cycles. And then their value on B cycles is determined by what the Riemann surface is. And this matrix is the period matrix of the surface. By the Riemann relations, it's symmetric, and its imaginary part is a positive matrix. The modular group is now the symplectic group that leaves this intersection pairing invariant. And so it has integer entries, and each matrix A, B, C, D is H by H, and it satisfies this symplectic condition. And the 1 forms and the period matrix transform like so. So how do we write down a Green's function and a measure? Well, actually, on a general Riemann surface, you can associate the Jacobian, which is an abelian variety. And the Jacobian is a torus. It's a flat torus. So on the flat torus, there is actually a flat metric. And you can make this metric canonical by asking that it be invariant under modular transformations, namely under SP to H. So you can define a canonical metric on the surface by pulling back this flat metric on the Jacobian under the Abel map. And that gives rise to a modular invariant and smooth canonical volume form on sigma, or Kähler form, which I wrote down here. So omega is the holomorphic 1 form, and this is its complex conjugate. and y is the imaginary part of the period matrix, which is, remember, positive. And so this is the inverse of it. H is the genus, and we've normalized it so that the integral on the surface is 1. So this is a very natural metric, which is in fact conformal because it doesn't involve any choice of metric, so to speak. So that's a natural candidate for a volume form on sigma. Now, there's also a natural candidate for the Green's function introduced by Arakelov in his study of the Mordell conjecture and the visors on Riemann surfaces and norms on the visors. And that Green's function satisfies, as always, the right-hand side gives you a delta function, but then because of the constant mode on the surface, there is a subtraction, which we choose to be this canonical metric. And then there's only one thing left. If determines G up to a constant, which you can normalize by asking that it be integrated into 0. So a natural generating function for higher genus modular graph functions would be to write down the exponential of these kinematic invariants with this Arakelov Green's function, and then take as a measure the product of the measures for each surface. So these integrals are absolutely convergent for s less than 1, an absolute value. So they're analytic near s equal to 0. They depend only on the surface, not on the specific period matrix chosen to represent the surface. So the modular invariant in other ways, another way of saying. And so one defines, so one can do a Taylor expansion at s equal to 0. And so we define the coefficients to be modular graph functions at higher genus. That can be one definition. Now, actually, for genus 2, the string amplitude is known, but it does not coincide with what we just wrote down. And the reason is as follows. The Green's function is fine, but the volume form, kappa, is unique when you consider the form on a single surface. But if you actually consider measures on a product of surfaces, there are other choices than the end power of this volume form on a single surface. So as I said, for genus 2 and the 4 graviton string amplitude is actually known, and it's given like so. So the exponential is there, but the measure is different. And so what is the measure? Well, it's a little bit more complicated. It actually depends on these kinematic variables S, okay, to linear order, and then a quantity called delta, not to be confused with a Riemann vector. So delta is a biholomorphic 1 form on sigma square, which is formed like so out of the holomorphic abelian differentials. So this is a quantity that's very specific to genus 2. You cannot write this antisymmetric combination down for higher genus. And so the measure is actually the wedge product of something holomorphic times anti-holomorphic. And this determinant of y is there to make it modular invariant. So the structure is similar to what we had guessed, but the details of the measure are actually different. So now we're going to be interested again in expanding this integral for small s in the power series in S. And what does the expansion look like? Well, you see that because y is itself linear in S, there is no constant term. There is no term that is independent of S. And in fact, the first term is quadratic, which is what I wrote down, still using these symmetric polynomials. Then there's a cubic term, a 4th degree term, and so on and so forth, of course, an infinite series. So the first term is just a constant on moduli space. So if you integrate it on moduli space, it just gives you the volume of moduli space. What's the next object? Well, actually, the next object we found out a long time ago is the so-called Kawazumi-Zhang invariant for genus 2. How can you write it in maybe the simplest way? Well, you introduce this mixed one form, which is the product of the holomorphic form in X and the anti-holomorphic form in Y, contracted with this matrix Y to make it modular invariant. And then the square of that, you integrate against the Green's function. This is not the way Kawazumi and Zhang originally introduced it. They introduced it as a spectral invariant of the scalar Laplace operator on the surface, but it's equivalent to it. And in fact, this invariant is also related for any genus, not just genus 2, is related to the Faltings invariant, which was used by Faltings in his proof of the Model conjecture. And this equivalence was established by de Jong. So in fact, this object, multiplying the cubic in the S's, is in fact a well-known quantity. Well, well-known to some of us, I guess. So what is the next order? Well, the next order you can write down, and it's given by this expression, which is of course more complicated, involves now 2 powers of the Green's function, and so on and so forth. So actually, to every order in the power expansion, you find a new genus 2, in this case, modular graph function. Okay, so can we say anything more about these modular graph functions? Well, this is a fairly new subject, so not that much, but let me say what we know. So to do that, I consider the Siegel, I'm now going to do this for general genus H. Consider the Siegel upper half space of H by H matrices, which are symmetric and have positive imaginary part. This space carries an invariant Kähler metric, which I wrote down here, where Y is the imaginary part of omega. And given this Kähler metric, there is in fact an invariant Laplace-Beltrami operator as well, which I wrote down here. Now, genus 2 moduli space is not, of course, the Siegel upper half space. You need to mod out by the modular group SP4Z and remove the diagonal of omega, which corresponds to disconnected surfaces. So now here is a result on this Kawazumi-Zhang invariant, which actually goes back to Kawazumi, and we proved it in an independent way. So this Kawazumi-Zhang invariant satisfies a Laplace eigenvalue equation. Laplacian here is this in Laplacian now in the Siegel upper half space for genus 2, with an eigenvalue which is definitely not of the form S times S minus 1, and also a right-hand side. So what is the right-hand side? Well, actually, this is an equation we consider on the Deligne-Mumford compactification of M2. And so this delta has support on the separating node, where the genus 2 surface splits into 2 genus 1 surfaces. So it's a delta function essentially on that node. And this equation was proven by the methods of complex structure deformation theory, namely, you consider these Green's functions as a result of considering conformal field theory on the surface, and then perform insertions of the stress tensor and its complex conjugate. Now, this equation has a funny benefit, which is that it actually allows you to integrate phi over moduli space. When we initially asked people who specialize in this, mathematicians, they said there is no way you could ever do this integral. But actually, having this equation, you can, because you use this equation to write 5 times phi as delta of phi plus this delta function, as I did here. But this can be unfolded by Stokes' theorem, and this can be evaluated. In fact, you can evaluate this integral. And not only that, this integral makes a definite prediction about a typical effective interaction that arises in the 4-point amplitude, namely the same fourth power of the Riemann tensor suitably contracted with 6 derivatives on it. So we make a prediction. There are other predictions coming from the properties of supersymmetry and S-duality in type 2b, and these match. Okay, now for these higher point functions, it's very difficult to make, I've now lost my clock. Okay, so I have, how many minutes left?
2 more?
2 more, okay, that's not many. So basically, you cannot investigate these functions much more beyond this, but you can investigate the generations. And I'll concentrate here on the non-separating degeneration, where one of the cycles tends to infinity. So when you do that, then in fact, the modular group reduces to the so-called Fourier-Jacobi group, which is SL2Z semi-direct product with Z cube. And the degeneration parameter sigma, which you use to make this degeneration, is not invariant. So when you expand these modular graph forms or functions in powers of sigma, what you get are not invariants, but actually covariants. What you get are Jacobi forms for genus 1. Now, there is, in fact, a parameter which is invariant, little t, invariant under this modular group for genus 1, defined in this way. And so the non-separating mode is now characterized by t going to infinity. And this is an invariant. So when you expand in it, you actually get invariance. So here's a theorem on the degeneration, and it tells you that there's a systematic expansion in this invariant parameter t, which is a Laurent expansion up to exponential corrections. And the Laurent polynomial has finite degree. Its degree is bounded from above by w and from below by minus w. So it's very similar to the expansion of one loop or genus 1 modular graph functions in tau 2. And the coefficients are, in fact, elliptic modular graph functions or single-valued elliptic polylogs. So that gives you a nice way of descending from higher genus to lower genus. In fact, this can be done not just from genus 2 to genus 1, but from a genus H to genus H minus 1. Well, I don't have the time to give you the ingredients of the proof, but it can be proven with the help of a Morse function. And the next thing I wanted to say is, so far before I considered the amplitude for 4 strings. Very recently, the amplitude for 5 strings was computed in full. And so, in fact, there are more modular graph functions that emerge now. I think I've defined all the ingredients. G is, again, the Arakelov-Green's function. Kappa is this measure on a single surface, and nu is this biform. And in fact, we discovered a simple algebraic identity, probably the first algebraic identity discovered at genus 2, which means higher than genus 1. And this, in fact, this identity implies a more complicated differential identity that was found by Basu a few years ago. So this industry of studying modular graph functions to genus 2 and higher is really just starting, but it promises to be as rewarding as the case of genus 1. And progress is being made. Now here I have a last couple of slides on actually integrating genus 1 modular graph forms, but I don't have the time to go into this. So I'm just not even going to start. I think Federico showed you yesterday that the tree level amplitude has this beautiful transcendentality property where you can assign weight -1 to S. and then the weight of the Riemann zeta function at an integer n is n, then in fact this entire amplitude has uniform transcendentality. And you can show, but it's much more complicated, that in fact something similar to that holds true for genus 1. And in fact, since I don't have the time to go into this, I gave an extensive lecture about this in Copenhagen last year. It's on my website, you can look at it. So then let me conclude. So the low energy expansion of string amplitudes reveals a rich structure of modular graph functions at genus 1 and beyond. Beyond, I think, is in the title of this conference. There are relations with Kawazumi, Zhang, and Falting's invariants. The systematics of the algebraic and differential identities for genus 1 are clear and well understood by now. And this is now also starting to emerge for genus 2. As I skipped over the integration over genus 1, I'll skip over this remark as well. But I'm going to conclude by saying that with this rather complicated analysis of the integral of genus 1 amplitude to this rather advanced order of 12 derivatives on r to the 4th, to that order is actually the first order we have two different invariants. And the reason is that you can write down two different combinations of invariant polynomials of the kinematic variable, sigma 2 to the cube or sigma 3 to the square. And now we can actually compute their coefficients. And note that their coefficients have to be proportional to zeta 3 square. The one for sigma 3 square is non-zero. The one for sigma 2 to the cube is 0. Is there an explanation for this? Not so far. The only remark I can make is that the first one you can think of as emerging from the square of tree level, but the second one you cannot. So is this a pattern? Is there a pattern? Why is there a pattern? This is unknown. And only now are we starting to explore this kind of high order. And so I think a lot more will be to be said about this. Thank you very much.
Thank you. So let's just take 2 seconds to unmute ourselves. And I see there's already a first question by David.
Yes, Eric, my question comes from discussions that we had in Copenhagen about the weight of Euler's constant, which we readily agreed was 1 because it comes along with a logarithm. But you also have to associate weight with certain interesting rational numbers. Could you say a little bit more about that?
Yes, exactly the slide I skipped.
Thank you.
So, okay, so here on this slide, which I skipped, I wrote down the amplitude for genus 1, not the whole amplitude, but basically the amplitude that contains the log of s, which starts at the origin for s equal to 0, and then the terms in s to the 4th. So now you can assign the same transcendentality weights that you did for tree level. S you assign -1, pi you assign 1, that's consistent. You assign to a log of a rational number in some sense, or something of weight 0. You assign the weight 1, so that's fine. Here we can have some argument, but I think it's pretty reasonable to assign weight 1 to zeta prime over zeta, and then minus this constant. But then there's a pesky term left over, 63 over 20. So by itself, this is a rational number, and this certainly does not have weight 1. However, one should really consider these amplitudes not by themselves, but as part of a generating function of all the orders that come in S. And then these numbers can actually be interpreted as finite harmonic sums, but now they are embedded in a generating function. And now you actually have the right to give them an assignment of a weight, which is not that of a rational number. It's a little bit, if you take a multiple zeta value of depth 2, then you can rewrite it as an infinite sum of finite harmonic sums times a certain weight, if you wish. And so then to reproduce correctly the weight of the multiple zeta value of depth 2, you need to assign that particular weight to the harmonic sum. So this is actually consistent, but you would not really be able to see it from this single expression. Where you can see it is actually the expression for the non-analytic part, but since again I didn't discuss it, you know. Does that answer your question, David?
Yes, beautifully. Thank you very much.
Sure.
Do we have further questions? I was actually wondering, you had these interesting identities and a systematic understanding how to generate them for genus 1. What's the prospect of repeating these developments for genus 2 and higher?
Well, the same methods don't quite work because, for example, here we use momentum conservation. So that's very special to genus 1. It has to do with the fact that the torus is invariant under translations. And that's, of course, not true for higher genus. But there is an identity. In fact, we called it a lemma in the paper that we recently wrote on genus 2 5-point functions, trying to get it here in this paper, the second paper of it. There's actually a lemma that that allows you to use something like translation invariance. So I think that idea can be rescued. Now, of course, you know, everything you do at higher genus is more complicated, but I think conceptually, I think it is, you know, I think we're quite hopeful that you may be able to make some progress.
Thank you. Any further questions? Okay, if not, thank you again.
Okay, thank you.